So first of all, let's try to see what exactly do you mean by quantum, right? So can anybody just give me a brief about what this quantum word itself means? What do you think about the word quantum? Anyone?
It's like an unit for like a proportion for energy or something like that.
Absolutely correct, right? So that is called as quanta, right? That's the smallest unit of energy,
Yes, a
right?
quantum. Yes.
So if you work in this space, you basically are referring to um, the smallest unit of energy, or particles which can hold that smallest amount of energy, right? And then another word is your computing, correct? So when it comes with computing, you're fundamentally telling that you're going to use this particle to perform computing, right? And what is computing for us, for the people of our age? What do you mean by computing?
So like performing like operations or anything like that.
Correct, right? All these operations which you perform, integration, multiplication, division, and so on and so forth. I don't know. There are thousands and thousands of different operations. So, some type of an operations, logical information processing which you perform, it refers to computing, right? So, when we merge these two things together, we are saying that we are going to use quantas or very very small particles to perform computing, correct? So, at a very abstract level, is it making sense? Is it all okay to consume this information? That can you use actually? Let me put it another way. Can you basically use electrons to perform your operations like addition, multiplication, integration, these type of things, right? So is it making you feel interested about this or not? Can you really think of it that okay, the world has reached to an age where you are actually going to use an electron to perform addition?
Yes, sir.
A set of electrons you will be using to perform, suppose, multiplication or integration, right? So this is what quantum computing is providing you. It is providing you a capability of using these small quanta particles. They may be electrons. It can be a beam of photon, right? So all these particles differently can be leveraged, right? So that's the idea. When you are going to use something which is related to quanta to perform computing, entire that space falls under quantum computing space. Okay. Now, having defined this, what exactly are we trying to do with electrons? That's the question comes, right? How we are fundamentally using, or any other particle or any other thing. So to put it in a very very referential or very very abstractive way, it says that any uh, mechanism which can use which uh, which can store information even probabilistically, that is fine. You will understand what I mean by this. Even probabilistically, uh, statistically, uh, and work on quantum physics, right? Or basically modern physics theory, right? Uh, So any mechanism. Now this mechanism can hold electrons. So there are some quantum computers which works with fundamentally on electrons. There are other which works on photonic. There are photonic quantum computers. There are some other quantum computers which basically work on saturated or highly stable particles in your the chemistry table, right? Those particles like xenon, which are highly stable. So there are certain type of quantum computers which work on these type of things, right? And then there are basically light wave or microwave uh, quantum computing machines. So there are many different ways of developing a quantum computer. The most famous one are these ones where electrons are basically used. Photonic quantum computers are used to store the information. But the idea underneath goes by this: the mechanism in which you can store information, even probabilistically, that is fine. and that entire structures follows quantum physics. If this can happen, you are basically on the right route of developing a quantum computing machine, right? So this is now, if you want to go deeper into this section, you can look into, and it's totally quantum physics topics. You can follow these, understand this, and try to get more knowledge how you're going to, what will be the meaning of information here, how that will be stored, how that will be understood by something as an electron. So you can have its entire physical properties. You have to follow Schrodinger's equation. You'll have to understand in what eigenstate that particular particle can fall in, and then so on and so forth. But let's talk about from quantum computing from a logical operational perspective, right? How we are going to perform logical operations. What is the mechanism which we will follow to perform logical operations on our systems, right? So let's try to create a reference between the two, and then maybe it will be more clear. So let's talk about something called as classical computing, or basically your very large scale integrated circuits, right? So, do you all agree that in all your laptops and computers which you are using right now, they have VLSI circuits in them? Yes or no? Guys, am I audible?
Yes.
Yeah. Uh, okay. So right now, if you see in your machine, in your local computer, there is something called as arithmetic logical unit, right? I think all of you would have read it, correct? It is called as ALU, right? Yes or no?
Yes.
Right now, ALU basically, how is ALU designed? If you see to the fundamental blocks of ALUs, these there are something called as these types of things would have seen, right? These gates, OR gate, NOR gate, AND gate,
When do this?
yes.
Yes.
So there are multiple types of gates which you have seen: AND gate, NOR gate, OR gate, NAND gate, and so on and so forth. So fundamentally, your circuits are designed using this. If I go further deep into this, there is something called as bit. That's the most smallest unit of your classical computer to store information. Yes or no?
Yes.
Right. So if I talk about a particular bit, can anybody tell me what exactly physically a bit look like? How this particular bit is leveraged or designed or manufactured, which is
A
actually
transistor.
absolutely correct. So it's a transistor, right? So basically it's a transistor, right? So a transistor basically operates on, in a bit, it operates on two modes, right? Either in the saturated mode or the off mode, correct? So when your transistor is in a saturated mode, that is, it is having a potential in it, it's having a current voltage in it, you say that I have stored information 1. When there is no potential, or when it is operating in a zero off mode, you say that you have stored information 0. Yes or no? Correct, right?
Yes.
So in this sense, you say that, okay, a transistor or a bit basically can store two types of information, either 0 or 1, right? Only these two information it can store. So if it is storing 1, it is in a saturation mode. If it is storing 0, it's in a off mode. So that is well defined. And just for the sake of your information, the distance between the layers of a transistor, this is right now, it is in 10 to the power minus 6 meter scale. That is why current systems are called microprocessing units. When the new technology will come, and we will reduce this distance to 10 to the power minus 9, we will have nano computers or nano processing units, right? So this is just for an information. Now, one thing is clear, that the bit is something which is the most fundamental unit of information storage in current classical system. So if this is what is there in the current classical system, what is quantum giving this? What is there in quantum in terms of, so we understood that, okay, you are using some type of a a hardware device. This hardware device is called transistor, and you are, if you want to make it you want to make your VLSI circuits very large, like VV LSI circuits. Basically, ultimately, you will have to reach up into some type of a nano processing units. So more the transistors in your circuit, more will be its information processing capability and storage capability, right? So this is how a particular classical units looks like, correct? Now, what's there in quantum for us? So quantum has something called as qubits, or it is also written as QUBIT as well. It's one of the same thing. Quantum bits, basically. The full form is quantum bits. Now, we have understood that okay, you are telling that quantum computers can be realized using many different types of quantum particles. They can be photons, electrons, light wave, microwaves, and so on and so forth. Whichever thing you can utilize is which falls under uh, a modern physics theory space and has some capability of information storage. Even probabilistically is fine. Basically, all are probabilistic. Then you can actually leverage and design a quantum computing machine. But right now, what we are talking it in terms of logical systems. So let's talk. So let's assume that we talk about a electron-based quantum computing machine. Okay. Let's assume that we will be using a single electron, uh, which we will use as a qubit. So we'll say, okay, one electron will refer to one qubit, and then we will understand how this guy is going to store the information. We have seen transistors store the information like this, off mode and the saturation mode. We will see how electrons are going to store the information, and probabilistically also. So I believe all of you would be familiar with your Bohr's atomic model, right? Where there is a hydrogen atom. It has, okay, let me not put it like this. Let me put it like this. It has a positive uh, positron and neutron, let's say neutron n, and then there is an electron revolving around it, right? So this electron basically is revolving around it. This guy is called as a hydrogen atom. You guys remember how hydrogen atom looks like? Is it fine, guys?
Yes.
Now, we all know that there are two types of rotations every electron which revolves around your atomic center, or basically the nucleus. One is its own rotation around it, which creates its own cloud, which you call as electron cloud. And we all remember that we have defined our clouds like S, P, D, F, right? So there are different mechanisms or in which these clouds are defined. We will see it later. But also, we also remember that the electron revolves around its own axis also. Yes, you guys remember it? Yes or no?
Yes, sir.
Okay. Uh, uh, so once you say, so let's talk about only this self-axis revolution. Okay, suppose this is your electron. Okay. Suppose this is your electron. Now we all know that electron revolves around its own axis. Either it will revolve clockwise or it will revolve anti-clockwise, right? You guys remember it? It has two rotations. Either it will have anti-clock rotation or it will have clock rotation. And another thing I will ask now. Can at a particular point of time, t equal to suppose t dash, anybody tell whether it's a clock or an anti-clock rotation? Can we tell this?
No,
No.
sir. Like, no,
Yeah,
sir.
I know. Yeah, I know.
Sir, because it's like arbitrary. Like, we
Absolutely.
can't predict that.
Absolutely correct, right? So because we cannot predict that, and this electron is revolving clockwise and anti-clockwise on its own axis, we try to put it in a mathematical formulation. What we say, so let's say I'm calling the clock rotation as plus and the anti-clock rotation as minus. Okay, and what I'm doing is I'm trying to put a information space that if the guy is rotating in plus direction, let's call it as plus, that is one bit. If it is rotating in an anti-clock direction, this is your anti-clock and this is your clock. Let's call it as 0. Okay, I will put it like this. If it is revolving anti-clockwise, clockwise, you call it as it is storing information 1. If it is revolving anti-clockwise, you say that it's having the information 0. But do you all agree that it will be revolving either in only either this or this? There is no other way for the electron, right? It has to revolve, correct? Yes or no? We don't know. It will be revolving 1, it will be revolving 0. That is fine, but it has to revolve. So let's associate some probabilities to it. Let's say P1 and P2. So we all agree that, okay, P1 plus P2 has to be equal to 1.
1. Yes, sir.
You guys agree? Correct?
Yes, sir.
Okay, cool. Now let's try to put it in a mathematical operation. So I say that suppose that okay, let's put it in the form of a vector. Let's try to introduce some vector theory around it. We call it as I will talk about this. It's a cat notation. I don't bother about it too much. It says that root over P1. Okay, not let's. I should not. Yeah. Okay. So let's say like this. It's direction 1 and it's direction 0. So what I'm trying to say is that Q1 chi square plus Q2 square is equal to 1, and this guy is equal to P1 and this guy is equal to P2, right? So is it safe to call this entire thing like this? Okay, let me put it in a way which you guys understand. Q1, Q2 like this, and Q1 square plus Q2 square is equal to 1. Is this fine? What I'm trying to say is that a quantum bit or your qubit is basically existing in two states. It is in state 1 with a probability of Q1 square. It is in state 0 with a probability of Q2 square. This guy is representative of state 1. This guy is a representative of state 0. Square of this, the moment you do a square of this, it becomes your probability. And I will tell you why this under root thing or this square thing is coming in another minute. But is this clear to all of you?
Yes, sir.
We can put it like this, right? Because we don't know in which state it is going on. So we just say that let's assume that this guy is in Q1 state, another guy is in a Q2 state. Okay. Now, let me put it in one more. Let me put something else. So if you guys are familiar with the concept of basis vectors, what do you think of this? Are these two things same? The above one and this one? This expression and this expression, these are same, right?
Yes, sir.
Correct? Okay, cool. Now, so this is your expression of your particular qubit. So qubit is basically, you can call it out as a particular unit or in your quantum computing mechanism which stores information probabilistically. The amplitude of the qubit around clockwise rotation chi square plus the amplitude of your information around anti-clockwise, the square of that amplitude, chi sum is basically equal to 1 because it's probabilistic. So Q1 square plus Q2 square is basically 1. Now, why specifically are we using this square term here? The simple reason is to allow more information to be stored in this guy. So if I say minus of iota square and something like 4 here, right? So basically, because of just that square, don't you think that I am getting more leverage to store information in imaginary space also? Guys, yes or no? because I'm using a square, and I know that square of this has to be a real number, because that's a probability, and probability cannot be imaginary. So what I'm taking is that I'm taking a, and I'm saying that okay, a square will always be imaginary. I will take care of it, but let me take a as an imaginary number. The square of it, I will do all the mathematics in such a fashion that the moment you square it, you will fall under a real space. But till that point, till this property follows, I'm okay to use imaginary values also. Yes or no?
Yes, sir.
Yes.
Right.
Yes.
The moment you are so the moment you are bringing in imaginary, you are basically increasing the memory dimensionality. Right. You are increasing the increased memory dimensionality space. Now you are basically having one more imaginary space also to store the information. That's the simple reason of bringing out a square, or a square, or basically square root, whichever way you want to interpret it, to bring that under consideration. Now, if you say so what will you will, if this guy is called q square, q1 square is called probability, then what will you call q1? It basically called as probability amplitude. It is basically called as probability amplitude. Now, probability amplitudes can be imaginary number also. So they basically can belong to, they can be real number, they can be imaginary number. Both are fine. Okay. But did you guys understand the fundamental concept behind what qubit is?
Sir,
Yeah. Did you guys
so how
understand?
can we realize complex numbers physically?
You don't have to, because physically you can only realize the square of that number. But internally, for your mathematical computation, you are realizing imaginary numbers, right? Only physical observation is your square of that particular number.
All right. So, and how many dimensions are we working with here then?
Dimensions, okay. You tell me, how many dimensions do you see you are working here with?
I mean, if we are allowing for complex numbers, which is
Absolutely.
a 2D number plane basically.
So yeah, it
So
becomes a 2D number plane.
for for two values, we are basically working with 4 dimensions, if I'm not wrong.
Uh, okay. So for one qubit, basically, if you see here, how many dimensions are there? 1 and 2, right?
Yes.
There are 2 dimensions. The third dimension is the imaginary dimension which you are bringing inside it, right? But this is your third dimension. Now, so if you will, I will ask all of you to now go ahead and read the theory of Bloch sphere. So Bloch sphere is basically a concept which fundamentally represents how information is stored in a qubit. How you basically store an information in a qubit. Okay, so this is how a Bloch sphere basically looks like. Whatever I have mentioned about, it's the basic theory behind the Bloch sphere to store information in a qubit. Now, this particular plane is your imaginary plane. Okay, and then there are two angles which are called as theta and phi. If I take a point up here, then this angle has one meaning, and the previous angle has another meaning. So Bloch sphere basically has 3-dimensional space.
Yes, sir.
But the moment you take the square of the probability amplitude, it will collapse into a real number. That is for sure, because that number has to be a probability. It cannot be an imaginary. Okay. So go ahead and read the Bloch sphere theory now.
Yeah. So may I interrupt?
Yeah, sure. Please go ahead.
I think, sir, we should move ahead, because otherwise I knew that this will happen. These things are not really. Again, we will go back into the same understanding foundations. So yeah, means we just lay down like most of the things.
Yes.
And then we will, so that we can reach to the point where we are more interested in.
Absolutely.
Yeah.
So
for the students also, I just request that I really understand that asking this complex question, like whether the complex numbers are real, but see, that's a 2 mathematical foundational questions, and that can be simply discussed that, okay, actually the complex numbers are just a tool to explain certain situations which you cannot explain through real numbers, but that is actually man-made, correct? It has nothing to do with, there is nothing like that. You cannot realize practical. So there is a lot of maths involved in it. So please don't ask such questions right now. Otherwise, we will be completely deviated from our objective. But then the instructor has to give some answer, correct? So this is my humble request, that just try to focus more on in this the practical aspects, and try to learn the theories with actions. This is also an art, okay? Because every time you go into that detailing, at the end of the day, you are doing a foundation course. Sorry to interrupt, but let's continue, sir.
Sure, sir. Yeah. So, okay. So having said that, suppose the next part is, suppose we have understood how the qubits are designed, then how you have used in your classical theory, right? You used all those transistors basically to design and develop logical gates, right? You designed NAND gate, OR gate, uh, AND gate, and so on and so forth. And the combination of these gates are called circuits, correct? In a similar fashion, in quantum computing theory also, there are many gates which fundamentally you can realize using your qubits. These gates are called as Hadamard gate, then poly X gate, X, Y, Z. All there are all these types of gates are there. Then there are rotational gates, right? Which provides you the rotations of your block sphere into multiple directions. And then there are gates like C naught gate is there, which is fundamentally used for information merging, and so on and so forth. So in quantum computing mechanism, these gates are used to design a circuit. So I will just plot a small diagram for all of you, just for the sake of understanding perspective. Okay. Sorry. So this type of a gate can be realized. This is a 2-qubit circuit. So fundamentally, any simple circuit, a quantum computing circuit, basically looks like this. So these gates which I've drawn here, these are called as Hadamard gates. If I just quickly write the expression of a Hadamard gate, it looks like this: 1 by root 2 in your first this thing, plus 1 by root 2 in your zeroth rotation, right? That's it. So this is how basically your Hadamard gate looks like, right? So if you want to put it in a matrix form, it's like you can just call it out as this. So this is the expression of your. It can be plus minus also. So this is how your particular Hadamard gate looks like. So in quantum computing, you can actually design and develop different gates based upon the kind of operations you want to perform, right? Then again, if I quickly, so this is how the theory of circuitry resembles from classical to quantum space. Okay, guys, is it making sense now? Yes or no? Hello?
So we can say that using Hadamard gate, if you are in 0 state or 1 state, first you basically reach to an arbitrary state where means it's like a mixed state where both the components are same. So usually in quantum computing, any circuit first starts with Hadamard gate, because your electrons are usually in either in 0 state or 1 state. So start any computation, first you have to put it in a mixed state.
Correct. Absolutely. Yes. So if you quickly see how your so if I try to write it again, your qubits, how they would be looking like. So this guy would be looking like this. Entire probability is 1 in 1 state only, as I mentioned, and it's like this. Now this guy can be totally in your 0th space with a probability of 1. Then you can apply Hadamard gate just to distribute the probability equally. Then you can perform certain other operations. Then what is this, right? So what is this? So this guy is basically called as your measurement. So just to give you everyone a quick idea, if you see on Google, you will see there is a huge big machine which they are building, and which these guys are calling it out as quantum computer. So what happens in this quantum computer is that they are actually putting these small quantum particles. Now this machine is cooled at a very very low temperature. If I'm not wrong, this is the approximate temperature, which the even below this also, and then they are putting almost zero gravity, right? Otherwise, these atoms will only be on the ground because of the gravitational force. So they are trying to make this entire thing a zero gravity, very cool. And then what they do is they perform these operations on top of these electrons, right? Or these quantum particles. When they perform these operations on these quantum particles change their state. How they change their state is they change these probability numbers which are associated with them, right? They change these probability numbers. Something happens to these probability numbers. I'm giving you a very very quick overview on top of this. Now but we don't know it, right? If you guys have read about Schrodinger's cat equation, the experiment, until and unless the box is open, you don't know whether the cat is dead or alive, right? So that's the point. When you put a measurement on top of this thing, this particular qubit, which was represented by this expression, will collapse. Either it will collapse in zero, or it will collapse in one. Either it will collapse in the zeroth state, or it will collapse in the any of these two states. So what you have to do? Suppose you make the operation and you try 100 times measuring it. Based upon these probability values, that probability will reflect here. Suppose this probability value, and I'm just putting the under root of this thing here, for just the square of the probability is 1, right? So let's say P1 is 0.37 and P2 is 0.63, right? So you will see that 63% of the time, 63% of the time out of 100, it collapses in the zero state, right? And the remaining time it collapses in the one state. So that is how you measure the values of your system, that how your qubit is getting constructed, correct? So this is the way, and there are multiple matrices, which again you will have to look into the system to see. These measurement matrices normally uses poly X. Now, when you will be reading about quantum circuitry, you will understand why poly X is specifically used, because it is taking a particular reflection of the state. Basically, when there is a vector, you take a cos theta around this axis, right? And you're making assuming this particular value only for your measurement perspective, right? So this is something like this. You will see. We can go into more details and we'll understand more about these things. But that is how these measurements are done. So that's the concept of designing a quantum computing machine. So there is a big machine, a lot of quantum particles inside it, a lot of operations you perform, and then you do a measurement. When you do a measurement, it will fall under either of these states, either P1 or P2 with a certain probability, and that probability can be understood by taking multiple iterations of measurements, and then you can see that okay, this measurement is around this, right? So that is how it would be realized, okay, in terms of actual numbers, to understand in which state your qubit is when you are developing that circuit.
So is it necessary for any algorithm to start with that all the quantum particles in the quantum computer should be in either in reset state, like zero state or something, so that we
generally
can
they are generally they are generally they are in this state, but to stabilize it, we just put something called as with something of this sort. We put like all the Hadamard gates we will put just to, this is called state preparation. So initially when the system is on, they generally are very random. Normally they are in either 0 and 1, but if they collapse, if you have taken a measurement, they definitely will be either in 0 or 1.
Yeah, but if we don't know what is their initial state, our whole circuit interpretation will be, won't it basically give wrong answer, because we don't know what we started with.
That's
Is
why,
it
sir, we will start with Hadamard circuits. Hadamard will distribute the probability equally. This is how the Hadamard gate looks like.
okay?
So it
So
will
you
force the
have
system to come into a equal
have a
probability state.
confusion. Any arbitrary state to this equal
Sir,
one in this equal distribution. If it was in any
sir,
arbitrary state,
uh-huh.
then
Sir,
apply
is it
Hadamard
for me?
gate.
Is it for everyone that sir's voice is breaking?
For you, sir.
Sir, your voice is
My
lagging.
question is,
Sir, your voice is breaking actually.
maybe somebody else can explain. My question is, if we are applying Hadamard gate on any arbitrary, we get the same state as the output.
Yes, sir, every time. Because Hadamard gate is meant to redistribute the probability.
Irrespective of what state we started with, correct?
Yeah. Normally, these quantum systems are either it will be in the zero state like this, or it will be in one state like this, something like this.
Yeah,
right? Either
because
of
in
two.
my
The moment you apply
my
Hadamard, you will fall under this guideline.
but in my understanding, if we apply the Hadamard on twice, let's say I applied Hadamard, then again I applied Hadamard. My
Then you will
understanding
be
is,
at that same state.
yeah, go back to same state.
Yeah.
So okay, means we'll see that, but that's just to know.
Sure. Sir. Yeah. So this is how basically your quantum circuits are designed. Now let's quickly look into other fundamental phenomena of it. So there is something called, so whatever you are doing till now, this plus sign which you are using, right? This plus sign whenever you are using, whenever you are mentioning any quantum qubit system, this plus sign basically refers to superposition. This is called as superposition. Okay. Why? Because you are basically bringing two basis vectors together and representing a phenomenon. That's the simple reason. Because you know that there is the quantum bit which is rotating anti-clockwise and it is also rotating clockwise. So you call these things as superposition. Now there is another property which is called as entanglement. And we will see all these things in detail once we start the sessions. But entanglement is a property which basically, if you will read, you will understand that it's a fantastic property of quantum physics, which states that the moment you entangle two qubits together, and the expression goes like this, something like this. This is your first qubit, and this is your second qubit, and then they become Q1 qubit, like this. If the moment you entangle two qubits together, you will never be able to separate them. They will always be together. Right? Mathematically, basically, when you perform an entanglement operation, it basically says that you are doing tensor multiplication. So you guys can go ahead and read about, if you already know it, that's fine. But you can read about how tensor multiplication is performed. Basically, you perform tensor multiplication on Q1 and Q2. Just to give a quick idea, suppose a quantum bit is existing in two states, that is 1 and 0. Another quantum bit is again existing in two states, that is 1 and 0. The moment you entangle both of them, you will actually end up in four states now, and those four states will look like this. There will be some number here, probability amplitude number, some again number here, 0, 1 state, some number, 0, 0 state, some probabilistic number, 1, 0 state, right? And if I say all these numbers as P1, P2, P3, and P4, again the square of all these will be equal to 1, right? So this is how fundamentally entanglement works. So you guys absolutely can go ahead and read about it. The expression of performing an entanglement is a C0 gate. So when you perform something like C0, where is that one? Circuit. So this particular operation which we performed, right? This operation here, it basically is called as a entanglement operation, and that is how a quick overview of how entanglement looks like. So now we have understood what we have seen. We have seen what qubits are. We have seen how these qubits are represented, We have seen how you create circuits about using them. We've also seen the concepts like superposition and entanglement, right? I'm just given a quick overview about all these things. Now, let's jump to what we can do with all this information, right? What all we actually can do. So I'm sharing a quick link with all of you, and I want you to open that link on your systems and see if you can access it. It's the first thing which will fantasize you to basically, this thing. So I don't think there is any sign-in required, but if it is, then you will have to sign in and see how it goes. Uh, so I'm putting on just embrace the chat. Here it is. I'm pressing. Okay, so if you go with, if you guys quickly open this link, you will actually see something like this, which is happening like this, right? Now you can actually activate a particular qubit. You see here, okay? If you see here, this particular qubit is totally at a zero state, right? It is initially like this. The moment I put a Hadamard gate here, where it is? Let's add it in here. I put a Hadamard gate here. You see, now it has the probability has been equally divided into two states. Let me delete this guy also because I'm just taking single qubit, right? Let me delete this guy also. Now you see, your probability has been divided. So that's what I was talking about, right? So if you guys can open it, whatever have. So this is the first place so for a play around and see how practically you can actually see these things happening. Is it all clear, guys? Does it make sense for a quick start? Hello?
Yes, sir.
Okay, cool. Now let me just...
Sir?
Yeah, please go ahead.
Sir, what was C there?
C is basically your C0 gate.
Okay,
Entanglement.
sir.
You can read about you can get started. There is a lot of theory here. If you find it interesting, please go through these things. There are many indications, explanations about how you can create your circuits, documentations, and stuff like that. Right? Okay.
This code, what is coming at the right side when we are actually adding up this gate,
yes, sir.
That is in QCIG-T,
Yes,
correct?
It's a Q sharp code, sir.
Q sharp.
It will Q sharp. It's a Q sharp code, but it will use Qiskit as a library to perform operations. It's a Q sharp code. Yeah.
So maybe I think the first there are many languages, but people can start with Q sharp to start.
Absolutely, and it is so interactive that you keep if you keep it like this, it will automatically write the code here, right? So that's how interactive this is. You can design your circuit, get the code, and go ahead with your code, right? So all those things are possible. If you go through this, all these lot of documentations here, it's a good start for basically anybody new to quantum computing, right? Now, having said that, let me quickly jump to give you again a very quick review about how we use all these quantum circuit and all this theory for machine learning perspective, right? So for machine learning operations, we all know that it's basically a optimization. Any machine learning algorithm is a mechanism of performing some type of an optimization to train a particular model, again to learn some data, right? Learn some data. So generally speaking, all your machine learning model looks like this. You have your data, you perform some pre-processing, you put your data into a model, and this model goes into some type of a reverse feedback mechanism based operation until and unless you get certain type of acceptable accuracies or KPIs, and then you are done. right? Yes or no? You guys would be building some deep learning, machine learning models, right? So this is the general mechanism of doing it, correct?
Yes, sir.
Cool, guys. So in,
Sir,
in,
yes,
in
sir.
quantum computing
Yes,
space
sir.
also, I will just brief you what exactly you will have to do. You will have to take your data, but this time you will have to perform some pre-processing on this data. Once you have performed some pre-processing, you will have to understand how you can put your data to QPUs. To put your data to a quantum computing unit, quantum processing unit basically, which is a QPU, there is something which is called as quantum embedding, right? So this is a new concept. I'll share some links right away with all of you to look into this. And this quantum computing, quantum embedding basically helps you to feed your information properly into these small quantas, right? Otherwise, your classical data is not acceptable directly to quantas, right? So that theory you will have to look around, then followed by again some type of a measurement you will put. You will extract these values, check these values based upon some loss function which you have created, and then you will again update the weights. Now, what is inside this box? Inside this box is your quantum circuit, right? And what you're training is you're basically training your quantum circuit. What you're learning your data. Whatever data you're putting in, that data you're learning, and what you're training is you're training your quantum circuit. So every quantum circuit, as I mentioned about it looks suppose like this. So X gate is basically rotation X, right? How much you want to rotate your qubit in X direction. So all these parameters like Y, then something called as Z, all these operations which you can perform. There are other type of operations also which you can find in the documentation. So these all operations basically are parameterized. That means that you can control from here your loss function, which is in a classical dabba, which is your Adam optimizer, X gradient boost, stochastic gradient descent, not boost, descent, sorry, my bad. Gradient descent, stochastic gradient descent, so momentum, and so on and so forth. All these optimizers basically will change the weights of your quantum circuits, which are parameterized quantum circuits. You can specify the weights in these quantum circuits and check the loss function, right? So this is a general, very, very quick introduction to how quantum circuits looks like, how they will be trained. Now, is it all fine? Will you be able to take it from here? Right? A very brief mechanism how quantum circuits learn information, right? Fine, guys? Yes or no?
Yes, sir.
Okay. So having said that, let's quickly look into what are the starting points for you to start building your journey of quantum computing. Now, Google has actually provided something called as quantum AI. Google has provided us a library which is called as CIRQ. We call it a CIRC, whatever you want to call it out. This library uses simulate. So, okay, now to run all these quantum machines, as Dr. Ashutosh already mentioned, we don't have real QPUs as of now, which are very, very proficient enough. There are something called as simulators, right? So simulators are basically a software which will install in your machine. They can come under wrappers of Python. That's also fine. You can just have to write pip install CIRQ, and CIRQ will bring in its own simulator, right? The simulator will actually work in your CPU only, but it will mimic quantum computing. QPUs. So it will be absolutely not fast. It will be not fast, but in terms of learning accuracy, in terms of training mechanism, right? It will follow quantum physics. So at least for these things, you can rely on the simulators just to check whether things are happening in right direction or not. Fast, definitely it will not be, because it's not actually a QPU. It's just simulating. It's just mimicking how quantum physics works, right? So all these, whichever SDKs I will tell you, they come with their own simulators. You don't have to go beyond something and do and install them. It will come as you just install the package, right? So if you see here on the right hand side, this is a way of, and Circ basically works in Python. If you see here, it's written here. So Circ is a library which is given by Google. It works in Python. You just have to import it like this, and this is how you are basically creating a simulator instance, which will help you to run all your circuitry. You can. This is the smallest code which you can see, and then you can uh, use CIRQ package to write quantum circuits, ask those quantum circuits to work along with your neural networks also. So let me mention that also. So currently we live in a hybrid paradigm. So what is hybrid paradigm is, you use your normal neural networks and you use your quantum circuits and you use both of them together to train your model, right? This is your loss function, and this loss function basically updates the weight of both of them, right? It updates the weights of both of them. So this is how basically you this is fundamentally how hybrid systems look like. Now it can be vice versa also, that your quantum circuit is before and then there is a neural network. So both are right. So this is one library which you can definitely go ahead and explore. If you just click it here, get started with Circ. It's a very neat and easy to implement documentation. If you will find it here, you can see how basic circuits you can create, right? It will tell you how basically it works out. There are predefined functions. You don't have to do much. Then you can actually look at, print them, visualize them, and stuff like that, right? There is another library which I want to introduce all of you, which is your Penny. It's a brilliant effort by Xanadu. Xanadu is the company which has developed this Penny, right? And Penguin again is a Python-based programming language, right? You can again install Penguin using a simple command like pip install Penguin. That's it, and it will be installed in your local machine also. It also comes along with a simulator, right? You basically don't have to actually get a real QPU for it. There is a simulator which comes along with Penguin when it is installed, and then there are a lot of operations which you can use to develop quantum circuits, right? If you go on the documentation part, I will just tell you templates, right? So as I was mentioning, there are mechanisms of uh, uh, putting your classical data into quantum system, that is called as embedding. There are multiple templates which comes along, like amplitude embedding, angle embedding, basis embedding, displacement embedding. So all these are styles in which you are feeding that information into a block sphere. If you will read around it, very simple. So just to give a quick overview what amplitude embedding would look like, it's like you have these amplitudes in your probability amplitudes, right? So you first normalize your every row and you just put it on the qubit with the amplitudes. Basically, you are specifying the matrix with the probability amplitudes. Just as simple as that, right? So that is the first of basic versions of your embeddings. You can read it through. They have given a very neat documentation, right? And then again, there are something like if you read it, if you see it here, quantum operators. We'll go to that later. Just click here. Yeah. So if you see on the quantum operator side, as I mentioned, look, these are different operators which are available: C naught, rotation X, rotation Z. So you are just actually telling on which. Now here wire will basically mean which qubit are you working upon. You will have to specify the number of qubits you will be working beforehand. If you will see, read the documentation. They are very simple. A lot of fundamental examples are there. There is a separate panel. I'll share this link also. By the way, don't worry. Share this link also here, so you can start your reading.
I will request either some student or sir you later to share all these links over our WhatsApp group as well.
Sure.
Maybe some student can help. Just collect it from here and share it over the WhatsApp.
Guys, you can do it, right? Okay, yeah.
Yes, somebody just say yes. Otherwise, how
No, no,
will?
no. They are writing. I will do that. They are
Oh,
writing in the chat, sir.
oh,
Okay. Thank
Sainath
you.
sir is
Yes,
saying
sir.
the student is not saying. Fine,
No,
sir.
sir. No, sir. They were doing so, sending links.
Okay, sure. Thank you.
Yeah. So, so this is
So
something.
just I have one doubt, and let me just
Okay.
clarify it for sake of everybody. So, as neural networks use gradient descent algorithm, correct?
Yes, sir.
And then what you are saying is that you can design circuits, quantum circuits,
Mhm.
according to the gradient descent algorithms, correct?
Gradient descent will help to optimize this quantum circuits.
Yeah,
Yeah, like update the parameters of this quantum circuits. Yes, sir.
but then what that quantum circuit is? Because
Quantum
my
circuit is.
then for what is the purpose of that quantum circuit? So, in my understanding, it was like a neural network requires gradient descent. Instead of
Yes.
running gradient descent in a classical manner, you design an algorithm for the gradient descent in quantum circuit, and then there you optimize, yeah, by constantly feeding and optimizing the parameters of that quantum circuit. If that is not the case, then probably I have not understood it correctly. So I just want more clarity there.
So gradient descent is it is a mechanism of updating the weights of the neural networks, right?
Yes.
So how it works is like if you can see the screen, this is your neural network, and it has its own weights inside it. All these weights are on the edges, right? And these weights will be updated with this algorithm. So what they will do, it's a algorithm is back propagation. So you feed the data. The data
Yeah.
will pass through this circuit, and it will commit here, and then you provide the output, right? Stochastic gradient descent will match it, your input with your output, and it will calculate loss. This loss, which is what you want to minimize, so it will basically do it along with this. So all these weights will be differentiated, and it will back propagate, and this operation is taken place using gradient descent. Like it's a descent algorithm, right? So it will just whatever weight it is identifying, it will the new weights, it will just take a small section. This will become your new set of parameters, and those will go in the algorithm in the back propagation mechanism, right? And it will update the weights like this. So every weight will be updated with its older value, and because it's a descent, so delta W and some Latin parameter like this alpha. Alpha can be some Latin parameter. So that is how your weights will be updated. So this becomes your new weights. These are your older weights. So this is how you constantly like forward pass and backward propagation keeps on going until the loss is minimized as low as possible. Right.
Yeah,
So this is
that
how.
is fine. So which
So
part we are replacing with
this
quantum
part,
circuit?
this part.
Okay.
This part becomes your quantum circuit. Hadamard gate, X gate, something again, something some
The neural network.
yeah, neural network part, absolutely. And then you put a measurement device here, and whatever comes out of this goes into your loss function calculation.
Okay.
It can further go into a neural network also, and then you can put it in a loss function. That's totally
So
depend
let's
upon your
say
design.
if somebody wants to design a 4-layer or 3-layer, whatever,
Mhm.
is it like that the already ready-made circuits are available on these platforms, or the one has to first think or
Both
design these circuits?
both options are open. They
Okay.
provide, like Penilyn provide a lot of templates
Mm-hmm.
which you can directly use. I will show you. So if I just click on install, so if you see templates, embedding templates are there. A lot of these ones. So these are predefined circuits,
Okay.
right? So if you see like this, these are continuous variable templates. You
Okay.
can
So
directly use them.
let's start
They
with,
comes with a entire design.
somebody can start with this example circuits with respect to the neural networks, and
Yeah.
then basically then adjust it, then train it, correct? So when
Yes.
we are training it, what are we saying? Are we saying that we are able to update the you can say weights
Of that
faster
circuit.
when we are actually doing in a classical computer? Is it like what we are saying?
Yeah, no, no. So because you are actually using a quantum simulator,
Hmm.
faster will not be applicable here because it's limiting
Let's
quantum
talk at
physics.
if we are doing it on actual.
Actually, it will be really, really fast. If you're
Okay.
using a QPU, it will be blastingly fast. It
Okay.
will just
So
go
that
and it will
means
just come.
one thing is if we are using the real quantum computer, the updation process of that quantum circuit, which is an
Yes,
actually replica of neural network,
yes,
classical neural network, in terms
yes,
of quantum circuit, will be faster.
yes,
Okay. But if we are doing in simulator, do we still get any benefit?
yes. Learning benefits you will get because your quantum circuits enable you to perform entanglement. And I want students to read about it. But entanglement is fundamentally a mechanism of dimensionality explosion. It is taking your data, which is in a d-dimensional space, and then and you are performing superposition also. Superposition and entanglement. These two things help in better exploration of very, very complex patterns. Because of this entanglement, right? So if I say, suppose I have four qubits, the moment I entanglement or entire information you're putting on this four qubits, but because there is the circuit has entanglements inside it, and there can be many entanglements like this. First entanglement itself will take it to 2 to the power 4 dimensional space. Now, because you're going to a higher dimensional space from a lower dimensional space, your complexity from you're basically moving from non-linear and trying to make your information linear, because in higher dimensional space, information will tend to become as linear as possible. And because now you're learning your information in a linear space, you're actually better learning it. In your neural networks, current neural networks, there is no mechanism of exploding the dimensionality. You have to work with the same dimensionality which you are actually having,
So,
right?
so if I have understood correctly, we are saying that the concept of entanglement, correct?
Yes, yes,
Even if it is not, you can say, as it is what we get from quantum mechanics, but just that concept itself, and when we are actually simulating a quantum computer over the classical computer, it's actually giving us a benefit in terms of the better learning, either in accuracy or in uh, speed, correct?
yeah. Speed is not on the quantum. Speed will
But
be on quantum
accuracy.
machine, but accuracy, yes.
Okay. So even without the system, the computer being running on the quantum computer, just because
Absolutely,
this concept.
because of this concept.
Okay, that's interesting. So I will request students to even compare that when they are actually they can train the model on classical computer and then on simulator, and then compare that on means like after training the same amount of time, whether they are getting better accuracy in QML, and that will be an interesting to see. Okay.
Okay. So this is another SDK which you guys can see. Okay, IBM I have already mentioned. So okay, there is something called IBM, which IBM provides a Python based mechanism also, which is I think Qiskit has a wrapper. Qiskit has a wrapper in Python. Yeah. So Qiskit has a Python wrapper also. If you see this, so you can use Qiskit in Python too. Again, if I write, there is an open source library of Qiskit. Uh, it's- they are putting all their information together. Uh, yeah, this is the one. So if you go on Qiskit experiments, uh, there are many things they have written here. You can still go on Qiskit experiments, curve analysis, data processing, framework. So let's see data processing. Oh, all of them are Python scripts only, right? So Somebody has written a discriminator, scalar discriminator, process library. Let me just, for you guys, I think QML will be the best point to start because that's easy. Let me just see.
So this is good that if somebody is interested in Python, then he can simply start programming using Qiskit Python wrapper.
Yeah.
Okay. So
Uh,
Akash is having one valid question,
yes.
and he's saying that see once quantum circuits have no memory, means what are we doing? Means are we changing the gate themselves to make new connections? Like when we're talking about neural network, we have connections, and then those connections are having weightage, correct? But now, when we are talking about the corresponding quantum circuit, what do we mean? I think, in my opinion, the quantum circuit will be in some state depending upon all the qubits are having in some state, and that state probabilities is inherently capturing that notion what you call weight. Is that right?
Um, So you are right. There is no memory inside it. So every time you submit your problem to a QPU, you will have to submit the entire circuitry also. You will tell that okay, this is the circuitry, this is the new weights. You process it and give it whatever results come out every time. Because he's right. There is no QRAM as of now. You cannot store your circuit at one place.
So
In
that
neural
means the
networks,
circuit state itself is memory, correct?
yes,
Whatever the circuit is, let's say if it is a 4-bit circuit, so technically the four all those 4 bits, whatever in that state they are as of now, correct?
yes. So as exactly, so that itself become a circuitry, and whatever you have written in your Python code, how you have designed your circuit, it will be submitted through the device into that. That is operation you have to do. Circuit is basically what some type of mathematical operations you have to compute, right? So just submitting that problem to a QPU and telling okay, do this and give whatever comes out. So there is no concept of storing your circuit right now in QPUs because QRAMs are not available.
So
Whatever you have to do, you have to measure it and it will collapse.
yeah, that is understandable. So Uday is saying that I suppose the parameters of the respective gates are being learned.
Yes.
So a general unary gate is parameterized. So what do we mean by a unary gate is parameterized? Means can we
Yeah.
focus on that?
So basically, if you see every operation which you perform on a particular qubit, this is how your actual this guy looks like. This is the expression. This is the expression of your actual block sphere. So you are storing this. So what you are doing is this theta which you see here, right? These are your weight parameters, theta and phi. These
Theta and
theta
phi are basically in Bloch sphere, the angle between the x-axis and y-axis.
Absolutely, sir. Yes. So these angles you are, if this is the point, this guy is your theta, and the reflection is supposed here. This guy is your phi. So these are the angles which you are changing.
Mm-hmm.
So that is what. So if I say that okay, I have learned something. I've used a single qubit and I've learned classification of certain points. That fundamental and this data point has suppose 2 classes. You have 50 points and of class 0 and 50 points of 50 points of class 1. Then basically in your block sphere, what you're saying is that you whatever circuit you designed on a single qubit, right? You applied some Hadamard, X rotation, Y rotation, and you have learned how much you want to rotate and you freeze them. You freeze those rotations, right? You have freeze those expressions. Suppose this is your X, you freeze that rotation. When you take it in an inferential space where you are actually seeing your output, you will see that all your uh, these guys will come here. All your these guys will come here on this block sphere. That is what you have learned. Whenever this type of input come and you apply this circuit on it, because it is belonging from class 0, automatically it will be a point here. Class 0 cloud will be here. Class 1 cloud will be here on that block sphere. Basically, that is what you have learned. right? Initially, suppose this was your quantum circuit. Let's assume on a single qubit, you are applying some X gate, then you are applying some Y gate, and that's all. Suppose like as simple as this, and you are performing some measurement. Initially, these weights were very, very random, and when you pass your data into it, uh, uh, this is your data set which you are passing 50 of class 0, 50 of class 1. When you pass this in on the block sphere, if you represent all of them, they were like randomly, all randomly they were coming. You were not classifying it correctly. But then you learn it, you learn your circuit, right? You learn what you want to fix these weights. And now, after a lot of learning, this is your same circuit but learned parameters. This is head amount. Now we've learned how much rotation you have to perform here, how much rotation you have to perform here. You have learned it, and you have freezed these. That this is what I will use.
So there
And
is
again,
that means there is a single one-to-one correspondence between the number of bits data points. Like if there are 10 data points, correct?
uh-huh.
Then do I need 10 qubit system?
Yes, sir. So that depends upon the type of embedding you are using. There are multiple embeddings. People I've asked them to explore. Amplitude embedding will actually use uh, the number of rows equal to number of qubits.
Number. Okay. So per record, you need one qubit.
Angle embedding, if I'm not wrong, it is 2 raised to the power n. So this n is your number of qubits. So different embeddings will use different number of qubits. How you want to represent that information.
Okay.
Right? And there is something called basis embedding. Just check. I'm not. I'm able to see. But this there is embeddings are of this shape also, this shape also. So all of are possible. But this basically depends upon the type of embedding we are using. That will actually specify how many qubits we actually want.
So let me just put it in a very simple way. Let's say there is a rotation operation, correct? Rotation gate also is there. So in the circuit, there are a lot of rotation, you can say gates, operations are there. Somehow we have learned that how much rotation we need to apply, correct?
Yes,
So
absolutely.
at the end of the day, when we are classifying, we are using the law of nature to put some of the electrons at one side and some of the other electrons at other side. And just to do that, we have learned that if this is your data, they will be this is all the parameters like inversions, rotations, and that means transformations. Once we apply, we will reach to that.
Yes, absolutely. Once you have learned it, then when you are feeding it data, when you will pass a road through that learned circuit, that point will be, if it is a class
Because
0, it
at
will
the
be
end of the
represented
day, you
like
are
this.
just transforming those electrons, photons, correct?
Yes.
You're just every operation is transforming them to
Some type of transformations you are bringing into the circuit. Yes, absolutely.
Yeah. Okay.
Okay. So, having said so, we have discussed about 3 different frameworks. Let me just quickly go to the document again. Yeah. So, I think for now, cloud support, because you guys are working on your locals only, it is not that much relevant. But let me just quickly give you an overview. So, there is something called as AWS bracket. If you guys have a dedicated AWS account, then you can leverage all these Penny Lane, Circ, IBM Cascade using Python or QCIG, everything on this AWS bracket for quantum, right? So if I open this, it's a quantum computing tool which it provides you a complete end-to-end pipeline for design and development of enterprise-based solutions in quantum space. We leverage Azure's mechanism, Azure's QIO, but in my previous organization, this was the one which we were using. You guys can go ahead and read it. I'm putting this link also here for your reference perspective. Then there is something called as Azure QIO. You open that too. QIO. There is quantum inspired optimization. Yeah. So if you see Azure QIO, let's say okay, this is one application which they have used for wind energy optimization, right? Optimize wind farm energy production with the Azure QI. So somebody has written a very niche block here for this particular perspective. Let me just see. Azure QIO is the what is our Azure marketplace? So, so this is what I did in my last organization. Uh, so it will be having a reference to that, but uh, yeah. So you can read through it. This is the white paper which it refers. Uh, you can read through it to see how. So these all are the. We use basically restricted Boltzmann machine to design it. This is the design of an RBM. Uh, Solution benefits. If you want to read it, how it basically defeats MCMC, we have given a lot of stats around it. How it was able to show the improvement. This is me here, right? So please go ahead and read it if you want. I will share the link of this also. Basically, it's good if you start from the base paper. There is a link to this white paper along with it, so you want to read it. So basically, Azure provides you a complete suite of uh, uh, optimizers. I will show you the list also for a reference perspective. Whoever works in OR space, interested in OR space, it's a brilliant space or point to start your research with, because the quantum annealing is beating your state of art simulated annealing, or for that matter, any meta heuristic methodology which falls under quadratic, not beyond that. If it falls under quadratic, even if it is a very, very hard problem to solve, quantum annealing is beating it. So if I just say list of quantum, is your QIO optimizers, let's see what comes. List of optimizations. So you see, yeah, Toshiba, okay, got this one. So this is again an important link. If you have a dedicated Azure account, you can follow these links to create your own Azure workspace. But these are fundamentally for optimization perspectives, and they are very, very niche in their form. So what I mean by that is, if you have if you really actually know what you are doing, then only go into this site. These are basically meant for optimization solutions only.
So in our some of the students in our team are also interested in optimization in finance related things. So I think this will be useful for them.
Absolutely, absolutely. So they support QHash also, but don't worry, you can use their APIs to perform using Python also. Not a big deal. I just wanted to show you. Okay, these are the underlying hardware providers who are running all these optimizers for them. Okay, so I just want to show you the list of optimizers we can have. Okay. So follow on the same page. Again, this is very, again, I will share this slide also. One should come. So, okay. Yeah. So these are all the optimizers which they are providing: simulated annealing, population annealing, parallel tempering, taboo search, quantum Monte Carlo, substochastic Monte Carlo. So these are all available using APIs, right? So if you want to use them, if you to be very honest, I have a limited understanding. I have understanding of population annealing, parallel tempering, and quantum Monte Carlo. Only three. Stochastic, what it is doing, I have no idea. Simulated annealing, anyway, I know. But few of them I know, few taboo search, like taboo search, I don't know how it works. So again, if you're using these mechanisms, you should be very, very assured. First, read about them, see how theoretically they work. It also depends, and it has come out in my research that you should know what you're solving, and then you have to select the proper optimizer, right? So that is how it works. So, okay, having said that, I think this is also done. Yeah. Now, I will just brief you about spaces in which you can look for quantum. So wherever you feel like performance is an issue in terms of complex pattern recognition, you can try quantum. In scenarios where anomaly detection type of scenario is there, you can try quantum. In scenarios where you're performing optimization, you can try optimization problems falling uh, under Cubo. You can try quantum. Uh, Image processing, again, that comes under complex patterns only, right? So generative AI, you can try quantum. There is a whole theory of quantum NLP, which I am also working upon. You can try that too. It's very fascinating. And guys who have an interest in NLP, if they will read about it, you will understand what quantum actually can bring in, which normal classical mechanisms cannot do. Right. So these are some spaces in which I will again copy this.